So now let's consider what happens if we add more greenhouse gases to the Earth's atmosphere. In the last climate model that we created, we assumed that there was enough carbon in the atmosphere to absorb all of the infrared radiation being emitted by the surface of the Earth. But would it matter and would it impact temperatures to have additional greenhouse gases in the atmosphere? To answer this question, we're going to add a second layer of atmosphere to our climate model. In other words, we're going to look at the scenario where we not only have enough atmosphere to absorb outgoing radiation from the Earth, we also have enough atmosphere to absorb the radiation that's being emitted from the greenhouse gases that absorb the Earth's radiation. So if radiation is emitted from the Earth and gets absorbed by the atmosphere, and if that radiation gets re-emitted upwards, there are enough greenhouse gases in the atmosphere to absorb it a second time. And that energy will either be emitted upwards towards space, or it will be emitted downwards towards the atmosphere underneath. This is actually how greenhouse gases behave in our climate system. And this is actually a pretty good representation of how our planet works right now. We currently have enough greenhouse gases to act like two layers of atmosphere in our stock and flow model. So let's go ahead and formulate this mathematically and see if it impacts the temperatures experienced on the surface of the Earth. First, we will depict our stocks. Now, first of all, we have our Earth stock, and we have what we will call layer 1 of the atmosphere, and we have what we will call layer 2 of the atmosphere. And we still have the same amount of sunlight passing through the atmosphere and striking the Earth as we did before. We still have the Earth warming and emitting radiation upwards. And we still have atmosphere above the Earth warming and emitting radiation both upwards and downwards. The only difference here is that in order to distinguish between our two layers of atmosphere, we will call the lower atmosphere A1, and we will use T1 to represent the temperature of this layer. Unlike the earlier model, the radiation emitted upwards from layer 1 is no longer going to escape to outer space. It's going to be absorbed by the second layer of atmosphere. The second layer of atmosphere warms until it emits its own radiation both upwards and downwards, using the same black body radiation formula that we've been using. To represent the temperature of the second layer, we will use T2, and this means that this layer is emitting sigma T2 to the fourth upwards, and sigma T2 to the fourth downwards. It's worth noting that the lower layer of atmosphere is now receiving energy from two directions. It's receiving a flow of infrared radiation from the Earth, and it's now receiving a flow of infrared radiation from the upper layer of atmosphere. Because it's absorbing more energy, we might expect it to warm as a result. Similarly, because our lower layer of atmosphere is warming, it's also going to be emitting more of its own radiation downwards towards the Earth, and so we might even expect the Earth to warm as well. Following the same procedure as before, let's write out a system of equations that will allow us to solve for temperatures in the steady state when all of these stocks and flows are stable. If we begin with the top layer of atmosphere first, we can see that the only flow into the stock is coming from the lower layer of atmosphere. So we have sigma T1 to the fourth coming in. This is equal to the flows leaving the stock. So we have sigma T1 to the fourth is equal to 2 times sigma T2 to the fourth. Like before, the flows upwards and downwards are adding on the right-hand side of the equation, which gives us our 2. The equation for the lower layer of atmosphere is just a little bit more complicated. Here we have two flows coming in. We have the radiation from the Earth and also the radiation from the upper layer of atmosphere. Like before, we have two flows leaving upwards and downwards from the stock as well. Our balance equation becomes sigma Te to the fourth plus sigma T2 to the fourth equals 2 sigma T1 to the fourth. Our third and final stock has the same flows that it had in the one layer example. It has sunlight coming in, as well as radiation from the lower layer of atmosphere. The stock only has one flow of energy leaving, which is sigma Te to the fourth. So our balance equation becomes omega over 4 minus A omega over 4 plus sigma T1 to the fourth equals sigma Te to the fourth. With the two-layer climate model, we have 3 equations and 3 unknown temperatures. And in the next video, we'll go through the algebra that we need to solve for those temperatures.